Okay, so yeah, so we are at lecture 22. So first of all, there was this query, which was a good question last time, and I just want to talk about, in fact, just this guy, right? Um, this chap. So the query was that this was a problem. How do we do this guy? M congruent to 3 mod 4. Okay, something is in work. So it was a good question. So here was the general term. Let me tell you what the issue was. This was the general term. So this was the general term, and the issue was the question was on M congruent to 1 mod 5 and or M congruent to 3 mod 5. So what I did was that I basically the real issue is this chap. The real issue in the proof is that m into m plus 1 over 3 may not be an integer. So two things basically I realized when I tried to resolve this. So first of all, what you do is you multiply by 3. So the I mean it will be if m is congruent to 3 mod 4 or 2 mod 3, then it will be an integer. If m is 2 or 3, it will be an integer. But if m is congruent to 1 mod 3, then there may be a problem. So first of all, we look at it like this. So 2m plus 1, and let me ignore this term. And this is 3 times 5k plus 4 minus m plus 1. And this whole thing is over 3. So first of all, one could look at this 3 and it divides maybe not this guy but this guy. So the real issue happens when m is congruent to 1 mod 3, because then this is not a division. This does not divide by 3. This is 1 into 2, right? So this is a problem. But then in that case, this 2m plus 1 is congruent to 0 mod 3. Okay, and the other is this. Um, so when so this guy 2m plus 1 over 3 is a number then. So then we can take m congruent to whatever. 1 mod 5 over here and see. But anyway, there is another issue that suppose, suppose 3 5k plus 4 is congruent to m into m plus 1 mod 5. Okay, and uh, m plus 1 over 3 is an integer. Then 5k plus 4 is congruent to m into n plus 1 over 3 mod 5. So this also you can prove. You can prove that if CA is congruent to CB mod something m, then this implies that A is congruent to B mod m if uh, if the GCD of C and M is equal to 1. So we use this guy. So but anyway, it's an easier proof to just look at the whole thing. So I'm just going to point out over here, if m is so basically the issue was that, you know, how are you taking just on the numerator? And to use just on the numerator, the issue was if it was an integer, then we can use this idea to do it on the integer. If it's not an integer, then actually we need to, you know, handle something about this guy 3. So we need to multiply, you know, we need to realize that 3 divides this guy in that case. But anyway, now if we just look at it again, and I'm going to do it in this color, and I look at both these terms together, for m congruent to 1 mod 5, this is 3 times 4 minus 1 into 2 over 3 mod 5. So now you can think of 3 multiplying through, and you'll get 12 minus 2, and you get 0 mod 5. And similarly, m is congruent to 3 mod 5, there's no problem actually. If m is congruent to 3 mod 5, then again you will look at this guy 3 into 2, that's 6 into 7, and this is 4 minus 3 into 4 over 3. So now this gets cancelled and it's fine. So here there is no issue. Here there was this issue, but you got this 3 to multiply through to get whatever you wanted. And here this cancellation is due to this. So I hope that is clear now. I think Ayush, you asked this question, right?
Yes, Professor, it's clear now.
Huh?
Yeah, yes, Professor, it's clear.
Okay, so okay, all right. So now let's begin our next agenda. So what I want to do is I want to start with symmetric functions. Now, I mean, there is more stuff than partitions that one can do, but it will be, um, I mean, it's getting into similar type of theorems, whatever we already did. And I thought initially that I will do a proof of Gordon's proof of Rogers-Ramanujan identities, but it's too complicated. So um, that was the thing. And then symmetric functions are some things which are very, very useful and very central to mathematics, and and to combinatorics. So I don't know if I'll be able to establish the connect with combinatorics so much. That would have required starting with symmetric functions right in the beginning. But hopefully there will be some connect. At least we'll get some kind of confusion about these objects. So Okay, and I'm going to hopefully follow this reference which I found online, and I won't tell you where, but I'm sure you'll be able to figure out. Introduction to symmetric functions and their combinatorics by Eric Ege, and it's a AMS student library book. If you haven't noticed, this AMS student library has got phenomenal books, and I would say this is a prerequisite to a lot of material in algebraic combinatorics and representation theory. So before I begin, so Ayush, maybe you can switch off your mic.
Sorry,
Um,
Professor.
uh, I I mean, this is something I'm going to share something very vague, but this was told to me by my professor. So I attended some lectures on symmetric functions by one really fancy guy, a chap called Anton Mellick. So Anton with somebody else had recently proved a really huge conjecture in combinatorics. And he's become so he got hired into Vienna, and he's a real superstar, and he's a really very deep mathematician. And what he was doing was he used so this was a conjecture due to Garcia, Remel, and Haglund uh, on and it seemed like nothing on earth. But what these guys, and it was very combinatorial, and it took like 30 years for somebody to prove it, and the proof involved huge amounts of algebraic geometry, uh, topology, and symmetric functions. So very big geometrical favor it had, and it had a combinatorial proof. So what he said was, and this is what his point of view, his philosophy was, and that is what he. So that's what I want to tell you, that why this area is turning out to be very important. He says whenever there is a symmetry or some kind of a group structure or symmetric structure, you look for some kind of a invariant or something to package that symmetry, to show that symmetry, to express that symmetry, and that is what is happening in various areas of knot theory, for example, where there's something called a Jones polynomial, and that is what happens in group theory, where you have sure functions coming up in representation theory of groups, of finite symmetric groups, and similarly Lie algebras, Lie theories, and so on. So the symmetric functions encapsulate the symmetry of the object or the space that one is studying, and that is why one needs to study them as a piece. And this is a very classical area. I mean, you'll find problems on symmetric groups from theory of equations and so on. Okay, so that's why it is important, but unfortunately, or we won't be able to see much of the application. But we'll hopefully, all I'm hoping for is to get some kind of intuition of these things, so that when you see them next time, you'll pick up really fast. Okay, S of n is again a set of, or rather the group of all permutations in In, and the book uses this as In. So what we were using In, it uses this. This is also very common notation. This first n natural numbers, and pi is a permutation, and say f x1, x2, so on up till xn is a polynomial with coefficients depend. Some people like coefficients in z or q or even complex numbers. So we will just stick to complex numbers. And pi of f is basically you apply pi on the symbols x1 to xn. So instead of 1, 2, 3, 4 to n, you permute the xi's. Uh, so pi of 1, pi of 2, and so on. So you get a permutation of these variables, and we say in in algebraic notation, we say pi acts on, or the symmetric group acts on f by permuting the variables. I mean, have you guys done some course in group theory? Anybody who hasn't done in group theory?
I haven't done a course, but I know a little bit of the theory.
Okay. So anybody who hasn't done anything and has no idea about groups?
Professor, I think the rest of us have done algebra 1 and algebra 2. So I think,
That means you know what groups are.
yes, Professor.
Okay. So anyway, it doesn't matter. You would have seen group action, and I mean the proof of Silo theorems involve multiplying by one element so that it looks like a symmetric group anyway, right? So Cayley's theorem rather. So in any case, let's see. Let me just do a few examples. So let's say f of x1, x4 is this guy, and g of x1 to x4 is x4 square. And we take 2 pi 2413, by which I mean that 1 goes to 2, 2 goes to 4, 3 goes to 1, and 4 goes to 3. And um, is there another one? Sigma. So these are two guys. Sigma is 1, 2, 3, 4, going to 4, 3, 1. Now what is happening? Okay. So let's see. Um, what is pi of f? So x1 square is goes to x2 square plus 3 x2 will go to x4 and x4 will go to x3 minus 2 x3 will go to x1 and x4 will go to x3, right? And what do you expect pi of f plus g to be?
Professor, one question.
Yeah, I mean,
Pi is 1 going to 2.
sorry,
Is 1 going to 2, or is am I picking
can't
it
hear
wrong?
you. I can't hear you.
Can you hear me? Hello.
Yeah, yeah.
Why is 1 going to 2?
I mean, this is just the permutation, pi.
I think I didn't understand the notation. I think it might be different.
I can't hear you. Say it again.
Professor, I was saying that the notation I think is a bit different than we've used.
Notation is slightly different from the usual, but in combinatorics we always permute. Suppose we are permuting 1, 2, 3, 4. We
Right.
have some permutation. So this is not a cycle format.
Okay. Okay. All right.
So cycle format is like this. This is like a 2-line or a 1-line format.
Okay. Okay. All right.
Okay,
All right.
so that is exactly why I wanted to do this thing, because if you read the book, then one gets confused.
All
So,
right.
so what is sigma of G, for example? G is sigma is 3x3 goes to 1 and x4 goes to 2. So sigma of G is this. And what about pi of sigma G? So you operate two of them. So now sigma G is this. I operate pi on this. So x1 goes to 2. So x2 and x2 goes to x4 square, right? And if you look at pi sigma, 3x2 x4. So what is pi sigma of G? So first we are doing pi sigma. So pi sigma means that uh, we multiply these two guys together. So 1 goes to 4 and 4 goes to 3, right? So pi sigma is 1 goes to 3, 2 goes to 3, 3 goes to 1, 2 goes to 1, 3 goes to 1 and 1 goes to 2, and 4 goes to 2 and 2 goes to 4. So if I apply pi sigma on G, then I will get 3x3 and x2 goes to x1 square. No, wait, G is something else. G is here. So 3x3 goes to 2 and x4 goes to x4. So the point being that these two are the same. Okay. So one can verify very quickly. So here is a notation. I use xn for uh, x1 to xn. Um, and proposition f of, let f of xn, g of this capital Xn be polynomials. So they're in C x1 to xn. Okay. Um, let pi and sigma be in Sn. Then um, pi of constant times a function is constant times pi of f, or C a constant. Pi of f plus minus g will be pi of f plus minus pi of g. And pi of f times g is pi of f times pi of g. This we haven't verified, but you can look at it, and if you multiply this by this and then whatever terms you get, each term, if you permute, it will be the same as pi f into pi g. So this takes some doing, and pi of sigma of f is equal to pi sigma of f. And I mean, it's so boring that I don't even want to give it as an exercise. So a C book is my. I mean, just think through it. If you can't see yourself believing it, then try it or see the book. Okay, and here is a definition. Uh, Pi fixes f if pi of f is equal to f. We say f is invariant under the action of pi. That's one. And f is a symmetric polynomial, not a function. If in variables xn, if pi of f is equal to f for all pi in S of n. That means that f is fixed by all permutations of S of n. Right? So this n sort of matches over here, right? Right here. And there are there's a prototypical example. I mean, today's job is basically looking at one particular example. So suppose I have x1 and f. There are n variables. x1 is a term. Then I have to have x2, x3, x4 plus x5, right? If this is a minimal term, and suppose I have x1, x2 as a term, then I have to have x1, x3, so on, xi, xj. This is like a minimal set which is required. And suppose let's do x1 square, x2. Then I have to have x2 square, x1. I mean x1 square, x3 plus x3 square, x1 plus 1. I mean, at least x2 square, x3 plus x3 square, x2. Depending on how many variables there are, you keep adding terms. So everybody understands what a symmetric function is. Any permutation of n will keep this as it is, right? And so some basic examples are here. I mean, I won't call them prototypical examples. Well, I have called them, but that's wrong. Basic examples. Okay, this business right here, there are other ways to look at it. One can say that f of x1 to, so let's say in the, well, let me switch any two terms, xi and xi minus 1. Just switching these two terms. This is the I minus fourth place and this is the ith place. If I switch any two, actually it might be better to switch n. Let me switch this guy. I switch these two, xi, xn, and I'll still get the same thing. And another way to look at it is that you switch any two. So this is ith place and this one is jth place. So instead of saying that every symmetric polynomial you can, since it is generated by the transpositions, you can switch like this. And one specific transposition is this 1n, 2n, 3n, so on. Right? And one remark to note that if we take any monomial, any pi, and apply it to this monomial, x1, a1, so I'll sometimes represent it like x raised per a, x2, a2, xn, an, then the total degree remains the same. So if I flick it any two, then the total degree stays same. So now what this means is that I can take any symmetric function, any symmetric polynomial, we can write it as f0 plus f1 plus so on, fk plus so on, up till some value, where fk is are the terms with the total degree k. Okay, so one can look at the action of Sn on some Fk, whatever it is. Okay, and that is where we are coming to one of the very central ideas of the symmetric function, that one can look at what is called the monomial symmetric function. So well, again, I keep, after today I'll be able to say symmetric function, but right now whenever I say function, you should think I'm saying polynomial. Monomial symmetric polynomial. Okay, this is so let lambda something k be a partition. Well, this k will get confusing. Well, I mean, it's not the same k as here. So we use the notation length of lambda is equal to k. The monomial symmetric polynomial m lambda xn is the sum of x1 raised per lambda 1, x2 raised per lambda 2, and so on, xk to the lambda k, and all distinct images of uh, images phi of this guy uh, for all phi belonging to Sn, and we take and 0 actually. Here we take uh, xj to be equal to 0 for all j bigger than n. What is n? So if the length of lambda is bigger than n, right, this m lambda of xn is taken to be 0. Okay, and we include 0 in here. Well, this is the monomial symmetric function. So this is very useful. I just want to remark that m lambda xn equal to 0 if length of lambda is bigger than n is very useful. So basically, if we have lambda equal to 3, 1, 1, so here I'm writing m lambda as this, and I just have x1 and x2. Then I'll start with x1 raised to power 3, x2 raised to the power 1. Then I need something raised to power 1, 2, but this is 0. So I'll get 0. This is the idea. So I'm restricting to lambda smaller than equal to. Okay, so let's do more. So M3311x4. Now this is the right set of numbers here. But in my example, I had x3 here initially. But anyway, so this is x1 to the 3, x2 to the 3, x3, x4, plus all permutations of these. All kinds of permutations of these, and if two of them get the same thing, you don't use the thing. So for example, if you have this thing 1 2 3 4 going to 2 1 4 3, so this term will give you x2 cubed, x1 cubed, x4, x3, right? So we just use one of them. We don't include this. So there is not 2 times this. So same issue with if you have 1, 2, 3, 4, and these stay wherever they are. So this will also give you the same thing: x2 cubed, x1 cubed, x3, x4. So if this happens, we do not include it. So the operative word is distinct. Okay. Then one more example. Suppose we have 5 variables and we have many terms. So we will have this term x1 cube, x2 cube, x4, x5 also will be there. There will be many terms. But if we take, something has gone wrong with my board. Could be from a sweat or something. Okay, so there are many terms here. Let's say x1 cube, x2 cube, x3, x4 is here. There could be x5 cubed, x2 cube, x1, x3, and so on. So you could have many terms here, but if you put x5 equal to 0, what do you get? All terms which have x5 will vanish, but all the other terms will still stay there. And the other terms will be part of, so if you put x5 equal to 0, you will still get M3311x4. And this is something which will be very useful to us also. Is that clear now? What is a monomial symmetric function?
Yes, Professor.
Okay, so any symmetric function, polynomial on Xn will look like this. So some x1 raised per a1, x2 raised per a2, and so on, xn raised per an. And then there is some coefficient here, right? And as I said, it is of this format, right? Take terms of this, and we use this notation when I say coefficient of a1 to an of f, I mean this guy, C a1 up till an. Okay, and if you take the space, well, this is the set of all symmetric polynomials in Xn. This is a vector space over the underlying field C. So this follows from the proposition we did, that C times this thing will also be a thing, and F plus minus G will also be a thing. Right. So this will follow from the first two items on this, and this is this guy. If you just take set of all uh, symmetric polynomials of total degree with terms of total degree k, so they're called the homogeneous of degree k, plus 0. If you take all this, then this is a vector space also. So if you add or subtract two of them, you will get again a symmetric polynomial of degree k, right? So this chap over here is everything here, and it's built up of these guys over here, right? And you can, I mean, if it's of one, I mean, it's a direct sum, right? Because anything of total degree k is not of total degree k minus 1. So our goal is to prove that these monomial symmetric functions actually form a basis for this. So we get to know what the dimension is. So this is finite dimensional. This is infinite dimensional. Anyway, so if lambda is a partition of K, I don't know if you use this.
Oh, Professor,
Yeah,
in the first remark, what is the notation that you have defined?
I just called this coefficient COEFF of A1 to AN
Okay.
is this number C, whatever that means. Sometimes I'll have to write coefficient of delta is equal to 1 and so on. Okay, so where am I? Uh, so this guy is a member of this del sigma, capital sigma K of n, the m lambda which we've defined. And the book, for some reason, needs to prove that this is a symmetric polynomial. I find it quite obvious. And um, this is obvious from definition, but book proves it, so you can look at it. I mean, if you want to really, I don't know why he proves it. I mean, the way it's constructed, it's clear that it is a symmetric polynomial. Because you're taking all the terms which are, all the distinct terms which are, after moving it via pi. And this is important to note that given A1, AN, or AK, whatever, A1, A2, blah, 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 there is a unique partition, lambda, so where lambda 1 is bigger than equal to lambda 2, such that A1, A2, whatever is a permutation of lambda 1, lambda 2, and so on. So, uh, what is the significance of this remark? We are looking at the definition of this monomial symmetric function, and what he's saying is that you take the sum x1 to the lambda 1, lambda 2, and then you permute all of them. Take all the distinct images. So from our examples, we saw that we just, you just need to permute, take one of them, which was from x1 to the lambda 1, x2 to the lambda n, and then we apply this. So what we are saying is that m lambda of uh, xn is the unique polynomial of degree uh, sum of the lambdas, such that the coefficient of lambda of this polynomial, so it's a unique polynomial f, is equal to 1, and the coefficient of mu of f is 0 for mu not equal to lambda. And this is for all. Does that make sense? So we're saying there's a unique permutation, which is there's a unique partition which corresponds to any permutation of numbers. So given a1, an, you order them in non-decreasing order. That's a unique partition. And then if you take m lambda of that, if you take m lambda, then that will cover all the terms of this kind. So if you have any other permutation, any other partition, then um, this function f m lambda xn, uh, the coefficient of mu of that is going to be 0. So anyway, what this means is, and this is again very obvious from this definition. So there is a proposition.
Professor,
Yeah,
we are considering the polynomial of degree mod lambda or mod x.
yeah.
No, is it mod lambda or mod x?
This guy,
Yes, Professor.
from the top it looks like lambda, and the bottom it looks like x. It's lambda. So this is lambda 1 plus lambda 2 plus sum of the
Right,
lambda.
makes sense.
So lambda is a partition of something. What is that something? And x is these variables. These capital X is the variables. Okay, so n bigger than 1, k bigger than equal to 0, and n bigger than equal to k, then m lambda of xn, where lambda is a partition of k, is the basis for lambda k of xn. So in particular, um, dimension of lambda k of xn is equal to p of n, which is p of n, p of k, number of partitions of. So n is the number of variables, and this is a partition of k. Okay, well, again, against my better judgment, I think. So the book says it requires a proof, but I think it doesn't require. I mean, this is a key observation. So summation c lambda m lambda xn, suppose for some lambda partitions in a set of partitions. So what am I proving? I'm proving linearly independent. Suppose this is 0. In this set, in a set, let's say S of partitions, for different lambda and mu, they have no terms in common. Yeah, because coefficient of mu of f will be 0, right? So this will imply that essentially all of them are 0. So either m lambda is 0, either the whole thing is 0, m lambda is 0, or c lambda is 0. So that does it for all lambda in S. So how about okay, we're going. Um, let me do an example. So what we're saying is that there is some, let's say C21, and we're just taking n equal to 2. So x1 square x2 raised power 1 plus x1 x2 square plus let's take another guy, which is this 3. So they are both degree 3. So here n is equal to 2 and k is equal to 3. And this is your guy, and suppose this is 0, they have no terms in common. This will imply that C21 is equal to C3 equal to 0. Right? So again, I don't think one needs to prove anything. The true meaning of this m lambda is that it is linearly independent. But anyway, the book is insistent that it wants a proof, and who knows what you guys will do to find out. So I thought I'll write down his proof. Now to prove spanning, let f belong to lambda k xk xn, right? So if f is equal to 0, then nothing to prove. If f is not 0, there is some non-zero term. There is some um, lambda such that x raised per lambda, which is x1 raised per lambda 1, x2 raised per lambda 2, so on. So, I mean, some of the lambdas may be 0. Um, is a term in f, i.e., the coefficient of lambda in f is not equal to 0. Is c lambda, say, right? So what about uh, so if one of these terms are there, by the fact that it's a symmetric polynomial, the m lambda, c lambda, m lambda of xn is a term, appears in f. Because you take all the permutations of this guy, this particular guy, and you're going to get that. So now consider f minus c lambda m lambda of xn. This is by induction. It's a smaller polynomial, smaller number of uh, terms here. So by induction can be written now, can be expressed as summation c mu m mu xn f minus c lambda m lambda xn, mu in some set, not set. And then we are done. So this is the key operative word. So at 0, there's nothing to prove, and then beyond that, there is a. So the remark is the dimension is independent of n, right? So the dimension is dimension of lambda k. Not, I don't know, this is lambda or sigma? This is lambda actually. Is this capital lambda or capital? This is capital lambda. Why am I calling
Yes,
it sigma?
it's capital lambda.
Yeah, I don't know why I'm calling it sigma. I know what sigma looks like. So this guy, I don't know why they call it sim. So the other guys, they usually call it sim. But there is always this confusion that they'll call it sim kn. So there's a little confusion in my mind between these two guys. So this is, in fact, I like this idea that he's put this. So, okay. All right. So then there's a proposition which we already noticed. If n is bigger than equal to the length of lambda, then this is a problem. M lambda of and you can do this thing and put many zeros. So this is, let's say there are j zeros. I mean, obviously A implies B by induction. So we don't have anything. So we have to prove, again, I don't think we have to prove much, but let's prove it. So proof. So let the length of lambda be equal to k, right? And x raised per lambda equal to x1 raised per lambda 1, xk raised per lambda k, right? So in either one, in either xn, so m, maybe if I move this here, this will be a different one. Okay. So I mean, this, you know, okay. Anyway, so m lambda of x1 to xn 0 and m lambda of x1 to xn are both non-zero. If this is the case, right? And if this is something, um, I mean, there have to be k of them, is a permutation of um, lambda 1, lambda 2, lambda k, then uh, the coefficient, so let's call this a, the coefficient of a in this guy is, I mean, I don't even know why I'm writing this, because to me it is completely obvious that these are true. This is clearly the case. Um, so what we are saying is that we are putting all the rest as zero. So, well, I think I know what they want to say. So they put an is a permutation of, put zeros, n minus k zeros, and then you take the coefficient of this guy and you put the last guy, whatever, it will still give you the same permutation. So that's what he's saying. Okay, so again, I really don't know why proof is needed. I mean, at some point I will just not give a proof, but here I just he bullied me into giving a proof. Like so. Anyway, um, where are we? So we know. So we know that this guy is a vector space. It's finite dimension. Its dimension is p of k. We know this guy is a vector space, but we don't know anything about its dimension. I mean, it's infinite dimensional. It's clear, but because it's a sum of all these guys, so this is okay. And m lambda of xn, they generated this vector space. So these are the basis elements. You take Ci whatever, and if lambda and mu are two partitions, right? What about m lambda of xn times m mu of xn? Now this is also a homogeneous uh, thing, right? This is in lambda k of n, where k is the length of lambda plus length of mu, right? So one should be able to write it in terms of the other guy. So here is a proposition. So until now we were just adding them. Now we want to multiply them. And for a proof comes a statement. So here's a proposition. For any lambda of mu and mu, a partition of lambda plus mu, and any n bigger than equal to 1, let a lambda mu n be defined as follows. So m lambda of xn, m mu of xn, since m mu form a basis, so I can write this product as a sum and let these be the coefficients. Okay, and the sum is over nu. So these are the things. And the proposition says that if n is bigger than equal to L lambda plus L mu, then A mu lambda mu n does not depend on n. So what's the idea of the proof? What he's saying is that suppose we are multiplying x1 to the a1 by xn to the an, and x1 to the b1, x2 to the b2, and so on, xn to the bn. And suppose summation ai is the same as whatever was there in lambda, and summation bi is the same as whatever this is, right? So if we multiply this, and we get x1 c1, x2 c2, and so on, right? Then of course summation ci will be this lambda plus mu. Now if n is bigger than equal to the length of lambda plus length of mu, right? Uh, the the right hand side, which is this guy, won't change. If I take anything bigger than xn uh, to be 0. So if I take everything else bigger than 0, it won't change, and neither will the reference side. So the point is that when you are multiplying over here, it's the length of mu or length of lambda which matters in this one, in just this one. And the number of variables should be more than that. Here, number of variables should be more than the length of mu. But if you're considering the product, then the length of n should be more than the combined length. Then it won't depend. Then it doesn't matter. Let's do. There's some example which I have done. Well, I can't make out what the example is, but some trivial example. So if I'm multiplying this guy, I multiply these two guys, then I get x1 square x2 plus x1 x2 square. So this is m21, right? And here it is m11, and this is m1. Yeah, so I mean, the issue is that if I have more than n equal to 3 variables, then it shouldn't matter. So this is no problem. Let's do one more. If you have one more variable, then it becomes x1 x2 plus x1 x3 plus x2 x3, and this one becomes x1 plus x2 plus x3, right? So if I have, so here it's okay, but if I have something like this, then if I multiply it, then I'll get x1 square x2 plus x1 x2 square plus x1 x2 x3, okay, and then I'll get x1 square x3 plus x1 x2 x3 plus x1 x3 square, and then I multiply this guy and get x1 x2 x3 plus x2 square x3 plus x2 x3 square. So what I get now is I get m21 in 3 variables, and I get 3 times m111, right? So I mean, if the variables is less than 3, then this one disappears. Here this is okay. This is here in both the cases, but if the variables is less, then this guy disappears. So this is not a very accurate. This is not very good. Not very accurate depiction of the product. This would be more accurate. And beyond 3, it doesn't matter, at least for this guy. Okay, so you see, you know what I'm getting at, that this term is missing when n equal to 2. Okay, this is going very slow. Anyway, the moral.
Oh, Professor,
Yeah.
I have a small question. So, when we defined m lambda xn, mu xn, when we defined the product, we had summation over what's this variable we called? Is this called v?
New,
I don't know the name.
new. This guy, na?
Yeah. So we are taking summation over nu, like a lambda mu to the nu of n and m nu xn, right? And then we are summing over all the partitions of mod lambda plus mod mu, right? And now in the case of x1 x2 plus x1 x3 plus x2 x3, like in our last example, on the right hand side we are only getting, like, we are not getting an m3 term, right? So does that mean that the coefficient a lambda mu for that particular partition is zero?
Um, so you're saying we're not getting which term?
M3 on the right hand side.
Yeah, I mean it's so the coefficient might be zero, right? I mean, in this product, do you see a product like x1 cubed? Answer is no. So the m3 term might be zero.
Right.
So
Makes sense. Thank you.
so all I'm saying is that when I multiply, it's again in some of those, in one of those vector spaces, and those vector spaces are spanned by m. I'm calling it new because I've called this lambda. I mean, I could have called this new, and then this would have been. And then these are whatever the coefficients are, whatever they are. And all this guy is saying is that these coefficients don't depend on n, provided n is large enough. So here we can see a real practical example. When n is not large enough, some terms don't show up, right? Like this term didn't show up. So anyway, the moral of the story is let's take infinite number of variables. And um, you know, the great idea is that beyond a point it doesn't matter. So you you can think finitely even though there are an infinite number of variables. So let me just define it quickly. A formal power series. So yeah, so this is a tablet issue. I figured out now. Uh, so I can only be blamed for my bad handwriting, not for the speed of writing. So formal power series with coefficients in complex numbers or even Q um, is, so this is the formal power series such that if f of a1, a2, so on is not equal to 0, such that if for only finitely many a1, a2, so on. So what am I saying here? What I'm saying is that you take the sequences n. So the indexing set is 1, 2, 3. I mean, you take an infinite sequence, and only if a term is non-zero, then there are only finitely many uh, uh, AIs. So each term is finite. So for one particular whatever, each term is finite. That's what it's saying.
Professor, could you repeat what is not greater than not equals to zero again? Sorry.
So this form. So let me write it down. Then you'll know what I'm saying. So what you can write is you can write this, and then you can do x1. Okay, I understand what you're saying. So, so this is the finite, this is the formal power series. It's a expression of this form where the sum is over all these guys, which belongs to n infinity, and only finitely many AIs are non-zero. That means each term is finite, but there could be infinitely many terms. And the formal power series are denoted, I mean, in some books, we see this kind of business. Or even infinite as formal series. Well, there are infinite actually. As a notation for formal power series. And the degree of the term in square is for any particular term is basically this degree. Okay, so is this clear? What we are saying is that there may be an infinite number of terms. The variables are x1, a1, x2, a2, and so on, but there are only finitely many of these. There are only finitely many of xi's which are there in one particular term. So you won't get an infinite product here. You'll get only finitely many over here. And that fits with our story. Each term, again, same story. Uh, Pi belongs to Sn, acts on each term by permuting the variables. So same story as before, and we define symmetric functions well, let me just define it. So let x k be a set of variables we say f formal power series or formal power series as above is a symmetric function in X if for all n bigger than equal to 1 and all pi belonging to Sn, gamma pi of f is equal to f. And again, pi of f is as defined earlier. So it's a symmetric function if for all n and all pi, it's symmetric. And again, now luckily we don't have to write the xn. So this is a vector space, say set of all symmetric functions, and gamma k is set of all symmetric functions, homogeneous of degree k. Okay, and definition, let lambda be a partition X is above. The monomial symmetric function is the, so m lambda is the sum of all monomials such that there exists n bigger than equal to the length of lambda and a permutation pi belonging to Sm such that pi of y is x1 lambda 1, x2 lambda 2, xn lambda. Well, yeah, where I mean you pad with zeros. Pad lambda with zeros as needed. So what are we saying? We are saying that it's the same old thing, except that the difference is that now for any, you want some permutation, any permutation from any symmetric group that will work. And if you look at it, it works out the same thing, because if you're only bothered about after some point on is all zero, then it doesn't matter. I'll take one more minute if you don't mind, or we can begin with this, because this will give me an excuse if you don't. The set m lambda partition of k forms a basis for lambda k. The dimension of lambda k is p of k. So proof omitted, and I think it's obvious, but you look in the book. When you look in the book, you will see the wisdom of why I've omitted it. Okay, any questions?